Thank you very much for the introduction, and thank you for having me here. I feel a little bit out of scope here, so I'm not a chemist, really not at all. I'm more kind of from physics background, and I love X-rays. So we'll be talk mostly about X-rays and a little bit about method development. And even so, I have a theoretical physics background. I came out to be almost an experimentalist. So yeah, but thank you very much for the opportunity to share our recent kind of tries and attempts to go into the energy storage materials, and maybe as a kind of almost an very philosophical start and a really very broad motivation kind of behind what is usually said about going into the development of new generation of energy storage materials. I just want to share kind of some thought which I have, that a society which is built on the knowledge-based technologies should function much better than a society which is built on natural resources. And if you have a thought, usually you will find some paper that gives some support to it. And indeed, there was some kind of study that for countries that they have switched from the natural resources to the renewables a few years after the index of democracy, so if it is a measurable quantity, it indeed grew a little bit. So, of course, I don't have kind of pretension to say that what we are doing will contribute here. So I'm too far from being such ambitions. But what I'm really confident about is that the materials which are at the heart of the energy storage, they're really beautiful, they're really interesting, and they're really worth study. And they're studied a lot. And yeah, and my kind of inner motivation was to contribute to the study by developing dedicated X-ray methods, what I have a kind of more background about with synchrotrons, X-ray electron lasers in the future. So just as an example of such a material is lithium manganese oxide. And it is a kind of, if one just looks at the structure at the room temperature, it is supposed to be cubic. However, if you would run a DFT on this particular structure, you will see that it is unstable. And it is also kind of understandable after some time, because here then the manganese should be in the oxidation state 3.5, so neither +3 or +4. And it is not what makes sense, really. So in reality, it is indeed 50% manganese in one oxidation state, 50% in another one. And the manganese in the oxidation state +3, it is also prone to the Yen-Taylor distortions. So, and actually what the structure in reality is a stochastic random distribution of manganese in different oxidation states with random Yen-Taylor distortions in all possible combinations. But on average, it looks like a cubic. But when you cool it a little bit, and this phase transition is really at the room temperature, so one can say it's really relevant. So if you run your Nissan Leaf just in winter, then the lithium manganese oxide would have really a structured order of the oxidation states and of the Yen-Taylor distortions regarding in a kind of much more interesting periodicities and structures, and would be really kind of interesting to understand properties of individual atoms here in a little bit more details. As I have said, I'm really coming from the X-rays, and the two techniques which are usually applied is either X-ray diffraction, from which you can get the positions of the atoms, so it's basically structure, or you take advantage that the X-ray energy could be close to the KH, and then you measure the absorption spectrum and you get the information about the oxidation states. But those two approaches, they're typically kind of disconnected, even so it's quite natural to do the same measurement simultaneously, and they really give a little bit different information. So here we have little contribution from the oxidation states, and here we get the spectrum from all the pieces incoherently. So we do not have access to properties of individual atoms and do not have access to knowing where the atoms with particular absorption spectrum is situated in the structure. So a kind of the degree of freedom which is available here is basically to combine these two approaches, namely to measure the diffraction spectrum across the absorption edge. Then the intensity of such break peak, it would be sensitive to the positions of all the atoms and to their scattering properties. And scattering properties is actually the absorption property and the refraction, which are fundamentally connected between one another via the Kramers-Kronig transformation. So in this way, one can get kind of much richer object, in this way, much more difficult to interpret. And the pain about how to get this information out of this observable, it will be basically the topic of the talk. And it's all nice to write down equations and to hypothesize that it is possible to solve the inverse problem, to inverse the matrices, to do some regularizations and so on. But the measure is really to do an experiment and try to do it in reality with all the noises, imperfections, and so on. So we have considered it as a first intermediate step as a trial beam time before going to the free electron laser, but it already gave so many uncertainties and reality checks that basically this talk will be just on this synchrotron measured data. And even so, we would like to understand the structure of the material itself, and we would really love to have a single crystal. Looks like that to grow single crystal of LiMn2O is not that trivial. So what we got from our collaborators were basically epitaxial thin films grown on a certain substrate. And already here came some kind of unexpected part. So I naively was assuming that the kind of in-plane orientation of the film and of the substrate would coincide. But just from the positions of the break peaks, we have seen that they are basically 60-degree rotated to one another. So I don't know if someone here is a kind of well-versed into the calculations of such kind of systems. I would be very grateful if I could get some insight why there is this 60-degree rotation. I don't know. But for us, it was actually quite a nice observation because then the peaks, the break peaks from the layer and from the substrate, they were not overlapping. So it was actually nice to measure. So the measurements were done at Petra synchrotron. So just very shortly, so we could change the intensity of the incoming light. We could control the temperature of the sample. And then with the 2D detector, we were able to capture distribution of the scattered intensity. And in this way, address several break peaks and see how they change when we are changing the temperature and when we are scanning across the KH. So just pure diffraction measurements, they have shown that our film is really nice in the out-of-plane direction. So one could see this fringes on the reflectivity curve, fringes on the symmetric break diffraction, and they give a kind of comparable thickness. However, when looking out of plane, there is much more ugliness and structure there. So it looks like in planes, a lot is going on, but it's not the main topic here. So what we could see that indeed, when we are cooling our sample, then at the HKL positions, which are in between the break peaks corresponding to the cubic structure, we have a peak appearing, which means that we have some additional periodicity in our system. And this agrees very well with the fact that the system undergoes the phase transition and these Jahn-Teller distortions and the oxidation states, they become ordered. It was quite known, so there are several published structures about it. And here it was just a kind of fun exercise to see what would be the DFT energy of the particular structure depending on with which method it was calculated. And nice trend, the more accurate the method, the lower is the DFT total energy. So indeed, the better you measure, the closer you are to the theory, or maybe it's also a coincidence, or on the other hand, one can say that DFT maybe works quite well here, which was not evident for me at the very beginning. Okay, so in this way, we can measure a set of such kind of break peaks, but then the next question is basically which Miller indices they have, since the next step would be to recover the properties. And here, basically, we had a kind of the first reality check and difficulty. So when we have our system in room temperature in the cubic state, we know perfectly where our break peaks are, and we can index them straightforwardly. But when we have our phase transition, then the system triples in two directions. And it, for example, can do it like this, and then we will have a set of additional break-peaks. Or, but actually, with equal energy and with equal probability, it can do the phase transition in this way. And then it will be a new set of break-peaks, or like this. So in principle, we have a kind of three possibilities with distribution of peaks in the reciprocal space. And we can just compare to what we have measured. And in this way, we see that from the same film, which we have seen is quite good and epitaxial, we have simultaneously several orientations present. So in this way, how I would imagine how the film may look like is maybe something like this. Maybe there are kind of several domains, so something like twinning, which are existing there simultaneously. And in this way, we have break-peaks from several orientations at once. But actually, it came out to be even more options since the parameters of the unit cell in two directions, they are very close. So actually, 90-degree rotation along one axis will give break-peak in almost the same position. So it's basically factor 4 more options. However, luckily, not all of them are very different. And actually, for this particular peaks, they are almost forbidden for the manganese. So for example, if you would consider some 004 peak, then the contribution of the manganese +3 and +4 is very close to 1, and same is for the total manganese contribution. However, if you would consider one of these reflexes that appeared because of the phase transition, that the total phase of individual manganese atoms are quite significant, but they almost exactly cancel one another. So what we see is almost forbidden reflex. So in this way, it is also quite sensitive to the differences of the scattering properties of the two manganese atoms. So it's actually quite nice. This weak reflexes, they're sensitive to the nuances of the structure, which we're interested in. In this way, we have collected the diffraction anomalous near-edge structure profiles over a range of reflections. But here, I would say, in contrast to the usual XANES measurement, where you just look at the profile and you can already start speculating this is pre-age and it's because of the transition to some free states, and here's oscillations due to the kind of next neighbors. Here, the profiles are quite different. They're quite different in shape, and also the shape is quite variable between different reflections. So somewhere we have a tick down, somewhere we have tick up. So we can first kind of try to understand what actually defines the shape of these curves. And if one just make a little bit simplification of the resulting expression, that then we can see that our signal is actually a combination of the usual scattering due to the all present electronic density. And when properly normalizing, we see that when the phases of the manganese almost close to one another, so it's quite a small number in the denominator, then the contribution from the lithium and oxygen becomes a kind of amplified. And it is just a phase. So in this way, the total quantity can become positive or negative, and then the interference between the usual scattering and the anomalous scattering, it could change sign. And this explains why sometimes we have the bending down and sometimes bending up. So it really depends on the sign of this resulting contribution. Yeah. Good. Okay. Yeah, and then we have a contribution due to the kind of contrast between two oxidation states. And when this contrast is changed, then it's actually a little bit of changes in the profiles here, but not as strong. Okay, so then the task here would be to try to extract from these data sets our absorption properties, or something what we are kind of more familiar with. And kind of a way to do this here would be just to discretize our particular spectrum And in this way, we also have to kind of somehow manage with the situation that we have contribution from the absorption and from the scattering, and so F prime, F double prime, and they are connected by the Kramers-Kronig transformation. And it's a pretty nasty connection between them since it results in quite long tails. So in this way, it was more convenient to set up some kind of background profile corresponding to the manganese in vacuum without any properties of the local electronic structure, and then just discretize the spectrum represented as in triangular basis functions, and then for each of these functions calculate the Kramers-Kronig, which is just some analytical expression, and then describe all of this spectrum as a set of the amplitudes for this basis functions and the properties corresponding to the overall electric scattering part. In this way, we can first try it on the high temperature reflection, where we basically know what to extract. So since we have a random distribution of atoms, the average absorption properties would be the same as extracted from the diffraction. And luckily, it is the case. So we are a little bit kind of confident that in this way, we can process the diffraction data and extract the absorption properties. And then we can go to our low temperature structure, and it's really interesting one. It comes out to have different number of Jentele distortions in different directions. So that's why it becomes orthorhombic. So A not equal B, not equal C. And also on top, it comes out that for a kind of one of the Jentele directions, there is still a kind of some freedom of the like polaron movement around this subpart of the structure. So the position, what is manganese 4, what is manganese 3 is not fixed. So it is on average manganese 3.25. So in this way, since we know that we have Jentele distortions and it is the reason why it becomes orthorhombic, then when dealing with the scattering, we have to take into account that actually the scattering properties should be anisotropic as well. So in this way, in addition to a kind of just, as it is typically done, assuming absorption as an isotropic property, here we have to treat the full matrix. So in some sense, account for the dichroism or birefringence effects. And it's also part of the information which we can extract out of the data. So taking this into account, the resulting contributions to the signal. So it has sensitivity to the structure, to the arrangement of atoms within the unit cell, and it has a sensitivity to the spectrum, so namely to the anisotropic part and to the difference between the manganese +3 and +4. And also on top, we have to take into account that there are these multiple orientations which I was describing. So in total, per a single spectrum, we have about 5 parameters basically that should be structure related. However, we cannot be sure that our thin film has exactly the same structure as it is reported for the single crystal. So basically we allow them to be freely fitted, starting as an initial guess from the known structure. Then a few parameters that describe the possible orientations, and finally 2 spectra that we are aiming to extract from our dataset. So this is how it finally worked out. So we had 6 reflections measured, and I would say if it would be 1 or 2, then of course we can fit it always, since we have everything free. But when we have at least 6 of them, and when we have a kind of more or less reproduced features for all of them here, then it gives a kind of at least some confidence that indeed we can extract or that these 2 spectral profiles, they indeed manifest themselves in the whole set of the data. And as a kind of, and as a result, basically what we get is really absorption spectra of the individual manganese atoms of the +3 and +4. And since it is really kind of mostly data analysis, no imprinting of any chemical information or any on top assumptions. And as a result, we have the manganese 3+ shifted to the left from the 4+. So it gives as it should be. So it already gives kind of some confidence that this approach is operationable. And as a kind of as a byproduct, we can also get insight into the structure. So, for example, here, as I have outlined, so we have a kind of 5 descriptors of the structure, like this effective scattering part and coefficients which are responsible for the contrast between the different manganese, and descriptors which are responsible for the anisotropic properties. And here I have first just compared 2 reported structures, which in terms of coordinates look really close. So the difference is somewhere in the 3rd or 4th digit. So these are the black points here. So even so, they look really close. They are a little bit different from one another. So in this way, it is not really surprising that the parameters which we get, they have some kind of deviation. So it shows a promise that we could be really sensitive to the quite detailed nuances of this structure. So this basically brings me to the conclusion that, yeah, these samples were good. We have observed this twinning-like domain structure, and based on more kind of advanced data analysis, I'm quite convinced that it is possible to extract the individual atom absorption properties out of the whole data set. And as I mentioned, it was basically a preliminary study before a kind of more detailed study of the dynamics. So the idea was to use this sensitivity to the individual oxidation states in order to understand what happens with the dynamics when one mimics polaron motion by means of laser excitation. So we have an attempt to measure it. This data analysis is ongoing. So I have to thank all the collaborators. So it's, you never go alone to the beam time. So it's usually a big list of people. And thank you very much for your attention.